All right, hi guys. For this next little unit that we're going to do, which is most likely going to be our last unit that we go over, we're going to talk about something called regression analysis. So, in some of your other classes, you've probably done a little bit with regression analysis. I know when I teach Algebra 2, we talk about linear regression with all this coronavirus stuff going on. There's a lot of talk about exponential regression. And in Algebra 2, I've also done quadratic regression. So basically, what regression analysis is, this is a measure of the relationship between two variables. So your relationship between your two variables can form many different types of regression. So like I mentioned, linear, exponential, quadratic. One way to think of it is linear. You're going to have a constant change. As one variable changes, the other variable should change as well in a constant manner. Quadratic, I often think of the example of throwing a ball. So as your time increases, you can model the height of a ball. So it goes up, it peaks, and then it comes back down. This coronavirus stuff is showing an exponential regression. So as time goes on, the number of cases are growing exponentially. So what we're going to focus on in statistics, as you can see down here, is a linear regression. Now, a little bit more up here, we are going to be dealing with two variables. So your two variables are referred to as your independent and your dependent. Whoa, can't spell. Person that says dependent, independent and dependent variables. So just a second here. Sorry about that. Had to plug in my computer before it died. But your independent variable is always going to be your x variable, and your dependent variable is always going to be your y. So we name them this way because the x, it can be whatever it's going to be regardless, but the y variable, we want to see if it depends upon the x variable. So for example, with this coronavirus stuff, dependent would be the number of cases, independent would be time. So time is moving by regardless. The number of cases depends on the time that elapses. Same thing with that quadratic one. Time is independent. The height of a ball depends on the time. So we're going to be looking at things like that. So one of the things to keep in mind is when you get a data set, one of the first things that you need to do, because it's not always going to come right out and tell you, is you need to determine which variable is independent and which one depends on the other. So what we're going to be looking at is something called correlation. Okay, we're looking for correlation between two variables. So correlation is a statistical relationship whether causal or not between two variables. Okay, so it's really important to throw in that statement of whether it is causal or not, because sometimes you will find a correlation between two things, but that does not necessarily mean that one of those things causes the other one. A very good example of this is there is a correlation between ice cream sales and murder rates. Now, does that mean that increased ice cream sales causes an increase in murder rates? Absolutely not. It probably has some underlying connection. For example, warm weather. People are out more in warm weather, so naturally you're going to see more human interaction, and sometimes in a bad way. So that would cause the murder rate to go up, as well as ice cream sales. So just because two things have a correlation does not mean that one of them causes the other. Now, when we talk about correlation, this is a really important part because it says it's a statistical relationship. So we're looking for something that we can actually measure. So correlation is measured in two ways, and that is by strength and direction. Okay, so we have two different things that we're going to be looking for: the strength of the correlation and the direction of the correlation. And we'll talk about those more down here with our correlation coefficient. So, like I said, for our particular study, what we're going to be looking at is linear correlation. So, linear correlation, this is just a relationship approximated by a straight line. And basically what that means is you're going to see a constant change. So as your independent variable increases, your dependent variable is going to increase or decrease in a constant manner. Okay, so now what we're getting into is what I consider to be the most important part of this whole regression correlation analysis. So we have something called our correlation coefficient, and our correlation coefficient is denoted by a lowercase r. Okay, so this lowercase r, what this does is it tells the strength and direction of your relationship. So when we talked about up here, correlation is measured by strength and direction, we have one specific value that tells you the strength and the direction of a relationship. So that means it is really, really important. So I'm going to draw this picture to kind of explain to you how we measure or what this R value means for us. So I've got this little scale here, 0 in the middle, -1 to +1. So R can only be between -1 and +1. So on your left side between 0 and 1, these are your negative directions, okay? 0 to +1, these are going to be your positive directions. So a negative direction, we'll see some pictures in a minute, but what that means is, let's say here's your graph. A negative correlation means as x increases, y decreases. So you have this negative slope of a line. When we have a positive correlation, as x increases, y is going to increase. So we have a positive slope of a line. So negative, positive, that tells you your direction right off the bat. Next thing that we have is strength. Now, this is not 100% set in stone, but in the classes that I took, in the books that I have seen, they kind of break it down this way. So we go from 0 to 0.2, 0.2 to 0.8, and 0.8 to 1. Over here, I'm going to go from 0 to -0.2, -0.2 to -0.8, -0.8 to -1. So these break up little sections that are going to tell the strength. Now, when you are right here in the middle at 0, if you have an R value of 0, there is no correlation whatsoever. Okay? If you go out to either end, +1 or -1, that means you have a perfect straight line correlation. The data can be represented perfectly by a straight line. Okay? So what we have in between 0 and 1 is all sorts of variations in strength. So the way I have always learned it is between 0 and 0.2 is considered to be a weak correlation. So there's some relationship there, but it's very weak. From 0.2 to 0.8, this is considered to be a moderate correlation. And anywhere from 0.8 to 1 is considered to be strong. And it's going to be the same thing on the other side. So what's going to change is you're going to have strength and direction. So this would be a weak positive, a moderate positive, and a strong positive. Over here on the other side, we would have weak negative, moderate negative, and strong negative. Okay, so we always have two things with our correlation. So let's see. Some other little pictures that I want to draw just to kind of make sure you are understanding these values. Okay, so for this first graph, let's say that we have our data points and they happen to fall in a perfect line like this. So what that means, because it is going downhill, it is negative, and because the points all fall in this perfect straight line, it is very, very strong. So with this one, I would say that it has an R value of -1. Now, that is really unlikely to have that perfect correlation. So more often, what you will see is your points are, still, you can get the idea that there is a straight line that will model this data pretty well, but they might not all fall exactly on this straight line. But I can still get a good sense for the direction it's going downhill, and my points are packed pretty closely to that line. So that tells me it is still going to be a strong negative. So I might estimate this to be about -0.95. Okay. Now, as your points space out further and further from that line, and they're not packed so tightly together, your R value goes down. So here I still have a pretty good idea that it's going in a negative direction, but my points are much more spread out. So I might call this one negative, 0.4. Okay, so moderate, but getting pretty close to weak here. Now we could see a lot of these in reverse going positive. Okay, let's say we have some points and they're all going in this nice straight line, then you have one that's not. So you're going to have this line and one point that's not on the line. So it is a very, very strong correlation and it's positive, but it's not quite perfect. So maybe 0.98. Okay. Now, sometimes you're going to have relationships that you have not much idea at all. So this would be one that's going to be pretty tough. A calculator will be able to tell you better, but maybe we're saying it is a positive relationship going slightly uphill, but it's a very weak relationship. So maybe we're calling this like 0.08, something like that. And then on some occasions, what if we had something like this? Can you get a sense of direction at all? And I'm going to say no, because, does it go diagonal? Does it go straight across? Does it go vertical? Does it go diagonal this way? There's not a relationship that we can form with this, not a linear one anyway. So this would be one where we have an R value of 0, which means there is no correlation between these between these variables. Okay. Now I want to show you the formula for calculating R. Is this. Whoops. Okay, so this formula, this is the sum of each x value minus the mean of the x values times each y minus the mean of the y values divided by your number of pairs minus 1 times the standard deviation of the x's times the standard deviations of the y's. So that's a pretty terrible formula, and I'm actually going to spare you having to do that formula by hand. So in one of the next 2 videos, I'm going to show you how we calculate R with the graphing calculator. Okay, so more videos to come on this.